resource allocation in private and public edge cloud systems. I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. So, collaborative edge cloud computing, here the edge nodes usually do not exhibit enough storage and computing resources when processing the massive data. Therefore, a collaborative edge cloud computing provides the users with computing services and requires the cloud and edge cooperation in satisfying the requirements of computing and storage resources. Now, this collaborative edge cloud computing scenarios, the edge node with limited local resources now can rent more resources from the cloud node and pay corresponding cost to meet the users' demands. Now, according to the nature of the cloud service can be divided into two different type of services. One is called private cloud, the other is called public cloud services. Now, regarding the private cloud, so when the users computing demands randomly reach the edge nodes, the edge node need to decide how to reasonably allocate resources between the cloud and edge nodes to satisfy the user's demand. Now, for edge nodes exhibits its own virtual machines to process users' demand. However, because the number of VMs requested by the users may exceed the edge node's capacity, so the edge node now needs to rent the virtual machine from the private cloud to scale up its capacity. Now, also the cost of private cloud changes dynamically according to its physical computing cost. So, the edge node need to dynamically allocate resources at each time slot according to the resource allocation policies. Now, in public cloud, the service provider, that is from the public cloud services, offers various pricing modes for cloud service. So, the edge node also needs to select appropriate pricing mode of cloud service for collaborative computing according to the user's demand. Now, the cloud service providers, that is public cloud service providers such as Amazon, Microsoft, provided three different pricing modes, each of which exhibits a different cost structure. The first one is called on demand, the second is called spot, third is called reserved. So, on demand requires no commitment, that is costs the most, but offers uninterrupted service, that is called on demand. The second type of service which cloud provider provides is called a spot. So, it is the highest of saving yet unpredictable and not for long term projects. Third type of service which cloud provider type of service is called reserve, 1 or 3 years commitment in exchange for discount service. Now, for on demand instance from the cloud service provider as a service, this pricing mode allows the user to pay with a fixed time granularity set by the platform, and the price is fixed in a long period of time. Reserved instance, in this pricing mode requires the user to submit the reservation time in advance and pay the corresponding reservation fees to have instance within the contract time. Now, it is applicable to the users with a large number of computing demands, and unit price is usually approximately 50% lower than on demand instances. The reserved instance has an option of customization with additional cost associated with it and called upfront cost. Third is called spot instance. The instance of this mode is obtained by bidding, and its price changes in different time slots, which usually used for short term computing demands. So, because the computing cost of the edge node changes dynamically according to their workload, if no strategic resource allocation exists when the edge when the collaborative Edge cloud computing provides the service. The computing resources in the edge node with a relatively low computing cost cannot be used reasonably, and its computing cost will increase. Therefore, reducing the long term operation cost on the premise of meeting the dynamic computing demands of the user is a key problem in CEC, that is collaborative edge cloud computing. The goal is to achieve the lowest operational cost under different strength of demanding amounts and computing time durations. So, the following sections in the next slides we will formally define the resource allocation problem in both private and public cloud scenarios. So, modeling the resource allocation problem in collaborative edge cloud computing. Now, let us assume that each time slot t the user submits a demand for the resources. The user demand can be represented as dt, d that is the demand at time t is split into dt and lt. So, dt represents the number of virtual machines which are being requested, and lt represents the duration of the service requests in the time slots at a time t. This is the demand, this is the user demand. Now, the total computing resources, that is VMs, owned by the edge node is, let us say, represented by the E. So, the resource is allocated to the user ET to represent the number of remaining virtual machines of the edge node. ET is the remaining virtual machines. So, the number of virtual machines which are provided by the edge node is represented by dt of E provided by the edge nodes. So, that is nothing but the requested dt minus which is being provided by the cloud, the remaining will be means met out of the edge, that is dt of E. And if let us say that edge is not providing, ET is 0, that is the remaining virtual machines at the edge at time t is 0, then the demand is not met, that is the virtual machines will not be allocated from the edge. So, the number of virtual machines which are provided by the cloud is represented by dtc. So, it should be noted that if the edge node has no available resources, here in this case, it will hand over all the arriving computing to the cloud for processing. So, when the resource allocation can be successfully performed on the edge nodes, each demand processed by the edge node will generate the allocation record like this. So, here in the previous figure we have seen the virtual machines which are allocated at the edge and the duration for that, and this demand and each demand by the edge node will generate an allocation record HT. So, det is the number of virtual machines which are provided by the edge nodes in this allocation, and LT is the remaining computation time of this particular demand here. So, when a new demand arrives, the resource allocation is completed and allocation record will be generated and added onto the allocation record list like this. So, H1, H2 and so on up to HM, which is nothing but the allocation record. So, when a new demand arrives, the resource allocation is completed and the allocation record will be generated and added to the allocation record list. Here, this is the allocation. H is maintained, the record list, allocation record list. So, allocation record list H is maintained to keep track of the completion of the user's demand. Now, modeling resource allocation problem in CEC. So, after the user's demands are fulfilled, the edge nodes need to release the corresponding virtual machine according to its record and delete the allocation record from the list H. So, the number of virtual machines that completed the computing task and are waiting to be released at the end of time slot t is denoted by nu t. So, nu t is nothing but the summation of DE t, where where I, that is for different time slots 1 to m, such that L I is equal to 0, that is H I is in H. So, the number of remaining virtual machines of the H nodes at time slot t plus 1 are the following: E t plus 1 is E t minus d E t plus nu t. So, in order to quickly respond to the user's computing demand, even if no computing demand is found, the machine still exhibits standby cost. So, therefore, the cost of the edge nodes consists of standby cost plus computing cost. So, standby cost of 1 VM in the edge node is, let us say, P e, and the computing cost of 1 VM in the edge node is, let us say, P f. So, the total cost of the edge node in the time slot t can be composed of the standby cost, that is P e multiplied by E t plus the computing cost, that is E minus E t multiplied by P f, that is computing cost of 1 VM in the edge nodes, and that amounts to the total cost, that is total standby cost and total computing cost E minus E t, because that standby cost is already detected. So, therefore, the remaining becomes the computing cost. So, computing cost divided by P f. Now, in time slot t, the cost of collaborative edge cloud in the public cloud environment includes the computing cost of the cloud nodes and the cost of the edge nodes, which is the following equation. So, here total cost of the public cloud is given here. In this case, the cost of the on demand instance, for example, if the public cloud is having the on demand instance then let us say x 1 is that demand, and the cost of customization of the reserved instance, that is upfront cost, and then cost of the reserved instance, then it is the cost, and the cost of the spot instance. So, here you can see on demand, then upfront, customization, and reserved instance, on demand instance, and the spot instance, and then the cost at the edge nodes, where x I is the service is used 1 and 0 is not used. So, the goal is to achieve the lowest operational cost under different strength of demanding amount and the computation time requested. Now, therefore, resource allocation as a decision problem, we have to see decision or the action denotes the ratio of virtual machines that will be provided by the edge nodes and the cloud nodes. So, A of t, that is the decision or the action A t. So, comprises of x c and x k for the private cloud scenario. That is the virtual machines, which x c means virtual machines which are provided by the edge nodes called x c, x k means the virtual machines which are provided by the private cloud. Now, A t, that is the action part for public cloud, here it remains the same x c, that is the virtual machines which are provided by the edge nodes, where the virtual machine which are provided by the public cloud is parameterized, where x k is the virtual machine provided by the public cloud, but k becomes which type of service of a public cloud is taken, that is what is parameterized, that is k is k 1 belongs to k 1, k 2 and k 3. K 1 is on demand instance service and k 2 is, let us say, reserved instance service, and k 3 is a spot instance service. So, let us consider an example where the users submit the following demand in 3 consecutive time slots. Say at the time slot 1, like here time. So, this is the first one, Now, this is the time slot, let us say 0, and here it is 1, here 2, here 3, here 4, here 5, this is t. Now, it says that in the time slot 1 and it requires 30. So, it requires 30 and for 2 time slots it requires 30 VMs, and in time slot 2 it requires 10 for 1. So, in time slot 2 so it requires for 1 time slot 10, and in third time slot now it requires 20, it requires 20 in 2 time slots for 2 time slots. So, here dt represents the number of VMs requested and LT represents the duration of the service requests. Now, assume that the time slot 1 is a starting time slot such that no VMs have been allocated a priori. So, assume that there are total 80 VMs present at the edge nodes. Now, given constraint is that standby cost of a VM at the edge node is 0.03. The computing cost of VMs at the edge node is 0.2, computing cost of the private cloud PC is 3, and unit price of on demand instance in the public cloud, that is POD, is 3, and it is 1.5, that is reserve instance, and customization cost is 800, and spot instance in the public cloud is 1. Now, resource allocation using private cloud. Now, suppose we have our own private cloud and a policy has been deployed to allocate the virtual machines as per the client demands, which outputs the following action. So, in time slot 1, now action x t for k is 0.4, 0.7, 0.8. Here x k 0 and 1 represents the ratio of VMs allocated from private to the total VMs requested. The remaining VMs is 1 minus x k are allocated the edge. Now, calculate the cost of collaborative cloud side computing, that is private cloud in a given instance cloud setting at 3 different time slots. Find the number of VMs that will be available at the edge node at the beginning of the 4th time slot. So, here if you see this particular solution of the problem which we have stated in the previous, let us say that E t represents the number of VMs available at the edge at the time, and let us say that it is 80 that was stated in the problem statement. At time t 1, the demand d t is of 30 for 2 duration, and action is that x 1 k is 0.4. So, the number of virtual machines which are allocated from the cloud is nothing but x 1 k multiplied by d 1, that is 0.4 is from the edge, 0.4 that is 1 minus point that is x k is 0.4 and multiplied by this 30, that is the demand, and it becomes 12. So, number of virtual machines which are allocated from the edge node will be d 1 minus that particular coming from the cloud, and that is 30 minus 12, that is 18 will come from the edge, and the number of virtual machines remaining at the edge will be 80 minus 18, 62. So, the resources can be successfully allocated from the edge, hence the allocation record will be generated here 18 2, that is for the edge. So, this is the allocation record. So, this is the cost at the edge, that is E 1 multiplied by P e plus E minus E 1 multiplied by P f. So, here you can see that point, if you see in the previous, so it is the standby cost at the edge node is, let us say 0.03 multiplied by 62, because 62 is not used. So, this is standby cost. And 80 minus 62 will be multiplied by 0.2, that is the computing cost at the virtual machines. That is nothing but 5.46 is the cost of the edge node. So, cost at the private cloud will be the cost of the cloud plus cost of the edge. So, that is the 12 is coming from the private cloud, and the unit cost is 3, and it is 5.46, that is the total cost is 41. Number of VMs to be released in N 1 is 0. So, the number of VMs available at the next slot will be the 62. Now, at the slot T 2, the demand will be D 2 and I 2, that is 10 and 1 for 1 unit. Now, the action for x to k is 0.7. So, the number of virtual machines allocated from the cloud is x k 2 multiplied by d 2, that is nothing but 0.7 multiplied by 10, that is 7. So, the number of VMs allocated from the edge node will become d e 2 is nothing but the total demand is 10 d 2, and the virtual machine from the cloud is minus that is 7,3 from the edge. Now, the number of virtual machines remaining at the edge node is equal to E 2 minus d E 2, that is E 2 is 62, that is available virtual machine on the edge, minus 3 which is required, that remaining will be 59. The resources can be successfully allocated from the edge node, hence the allocation record will be generated. In this manner, allocation record now will have 18 1 and 3 1. Now, the cost of the edge will be E 2 P e plus E minus E multiplied by P f, that is E 2 is 59, standby cost is 0.03 plus 80 minus 59, that is being given from the edge, that is 4.2, and the cost of the cloud will be from the edge. So, that is 7 multiplied by 3 and 5.97, that is 26.97, and this will be the allocation record, and the number of virtual machines waiting to be released here is now the first time slot also will be finished by the end of the second time slot. 18 will be released and 3 will be released because, and that is 21. So, number of virtual machines available at the next time slot, that is 3, will be E 2 plus N 2, that comes out to be total 80 will be available again. At time slot T 3, the demand will be D3, that is 20 for 2 duration, and the action is x3. For x3 is k is equal to 0.8. So, number of virtual machines which are allocated from the cloud is x3 divided by the demand, that is 0.8 multiplied by 20, that is 16 will be met from the cloud. The remaining is 20 minus 16, that is 4 will be from the edge. So, the number of virtual machines remaining at the edge will be 80 minus 4, that is 76. So, the resource is successfully allocated from the edge node, hence the allocation record will be generated in this following manner, that is 4 for the duration 2, that allocation record, and the cost of the edge node will be x E3 PE. So, that comes out to be, and E minus E3, that is 80 minus 76, that is 0.2, that is. So, standby cost plus the cost of the edge comes out to be 3.08, and the cost of the cloud will be now DCPC, that is 16 multiplied by 3 plus the cost of the edge is 51. So, total cost is 51.08, and the allocation number of VM waiting to be released in N3 is equal to 0. So, number of virtual machines in the next slot will be 76. Now, similarly, we can see the resource allocation using public cloud setting with a new policy that outputs the following time slot. Now, here it is parameterized public cloud. Now, here you have KT and XT, where KT is parameterized, whether if it is 0 then it means on demand, if it is 1, 0 means on demand, 1 means it is reserved instance, and 2 means spot. So, now the query is to calculate the cost of collaborative cloud side computing, that is for the public cloud in the given public cloud setting at each of 3 time slots. Assume that same demand were met by the client and that no customization is performed on the reserved instances. So, at time t1 the cost calculation for the edge node will remain the same as calculated in the private cloud. So, the cost at the edge node from the previous case, that is C1 PE plus E minus E1, that is PF, is 5.46. The cost of the edge public cloud is C1 public, then D1 of a, and then it is considered cost of the reserved instance only here in this case, and plus C1 E. So, that is calculated over here. Now, for time slot 2, that particular calculation is again, that is E2 PE plus E minus E PF, and that is nothing but a public cloud, that is the cost of the on demand instance only, since the time slot 2 is allocated for on demand instances, comes out to be 26.97. Now, coming to the third one, here the third one is the spot instance, and that cost comes out to be 19.08. Now, long term optimal resource allocation decision making, we have seen that the computation cost of the cost function at each step. However, we would like to minimize the long term optimal resource allocation objective over t steps. So, here t is equal to 1 to t steps, and this is the cost of private and public. So, we shall model the resource allocation problem as Markov decision problem, which converts the cost, that is minimization problem, into an equivalent reward maximization problem. So, Markov decision process is a discrete stochastic control process. It provides a mathematical framework for modeling a decision making process where the decisions were made at each discrete time steps. MDPs are useful for studying optimization problems solved via dynamic programming and reinforcement learning. So, Markov decision process MDP is a 5 tuple SAPR row, where S means set of states and A means the set of actions, P is the state multiplied by the actions multiplied by state. So, that means given a state, given an action, it will make a transition and another state is represents the transition probability, where P s being the probability distribution over the next state. So, P s S by S comma A is the probability of making the transition from state S prime from S through the action A. So, R, so that was the transition probability. R is represents the reward function. So, reward function again is S by A by S, and it gives a reward function where R t is R of S t, A t and S t plus 1 being the reward obtained by moving from state S t to S t plus 1 via the action, and rho represents the initial state distribution. Additionally, S prime represents the set of final states. So, the name Markov decision process refers to the fact that the system obeys Markov property, that is, the transition only depends on the single most recent state and the action pair and no prior history. Now, using the Markov decision process, let us understand about reinforcement learning. So, reinforcement learning, the environment agent interaction is represented by Markov decision process, where the agent can observe the environment, that is state S, and take the decision, that is action A. So, objective is to learn the optimal policy that maximizes the expected return or sum of the. So, type of policies are deterministic policy and stochastic policy. So, reinforcement learning, that decision process, let us take this particular trajectory at the beginning of the decision process at time t is equal to 0. The environment assumes one of the states from the initial state distribution, and during each step t observe the state S t, decide the action, that is A t, and make a transition to the new state with the probability to reach this S t plus 1 new state, receive the reward and terminate if the final state is reached. So, obtain the trajectory, that is S 1, A 1, R 1, S 2, A 2, R 2, S t, A t, R t and so on up to S t plus 1. Discounted trajectory return is nothing but R t means the reward function at time t, and then it is the gamma. So, the probability of the trajectory is the probability that an agent using the policy encounters a trajectory t. So, the probability can be derived as this transition on S 1 with the policy pi and the probability of S 2 reaching from S 1 on an action A multiplied by again the policy and then probability S 3 and so on. So, it will be total the multiplication or a product dot product of this particular policy and the probability and expected return. If you can measure out of that particular trajectory, probability of a trajectory, it comes out to be expectation. So, reinforcement learning objective is to find an optimal policy, that is pi star, that maximizes the expected return. So, what is that policy? What is that policy that maximizes So, that is nothing but an argmax. So, that set of policies which gives the maximum return k. Now, let us consider the value function. State value functions nothing but an expected return starting at state S. So, these are defined as an expectation of that trajectory function drawn for that particular policy, that is S I is equal to S, that is starting from, then state action value function expected return is starting from the state S and taking action A given by the q states, q values q S comma A, that is nothing but an expectation. Advantage function is how better is to take that action A in the state S compared to the other actions. So, that is an advantage function is the q value of S A minus V of S S, that is state value function, that means how much it has. Now, q value function on this optimal state action value function. So, the state action value function that gives the maximum expected return starting at state S and taking the action A and then following the optimal policy thereafter, that is the optimal q values of S A. So, optimal policy is the policy that will always select whichever action is the best, maximizes the expected return starting at state S. So, the relation between optimal policy and optimal state action value function, we obtain the optimal action A star using q star as follows. A star is nothing but argmax q star S A. Now, coming to the Bellman equation for optimal state action value function, that Bellman function is the optimal state action value function is nothing but an expectation of an reward S A and the gamma times that maximum of q values, q value function, that is S prime A prime. Now, let us take this example of a q value function through this particular example. Now, here the MDP states are A, B, C, D, E, F. It is a 5 tuple reinforcement, it is a 5 tuple, that is the states are A, B, you can see 1 A, B, then C, D, E, F. These are the set of states. The action are two actions A 1 and A 2. The discount factor gamma is equal to 1 and the transition is deterministic. So, let us see about the dynamic programming. You are starting from the last stage where the q value of final state F with star is equal to 0. Now, so you go to each predecessor node and update the q values using q star S comma A with using this Bellman equation. So, the remaining, so you can see here now that q value of D and q value of E is calculated as 1 plus here can 1 plus maximum of the q values of F A. So, that becomes 0, that both of them will become 1 here in this case. Now, after reaching D and E computation, now go to the predecessor node and update the q values using that Bellman equation which is shown. Now, here for there are two B and C we are going to calculate for the remaining B and C. So, for q value of B now is action, if it is taking the action A 1, that is 4 plus this q values, and if it is taking the action let us say A 2, that is 3 plus 1, 5 and 3. Similarly, q c. So, you can see that this is having the higher value. So, it will be retained. Similarly, for C there are two actions A 1 and A 2. Now, A 1 will give the 6 plus the maximum, it gives you the value 7 q value, and q value by action 2 is only 3. So, it will be selected. So, you can see that the action will be for, if it is in B, action will be A 1, if it is C, the action again will be A 1. Now, we are going to predecessor A. So, for A there are 2 actions, 2 and 1. So, if it is taken A 1, then the value is 7, and if it is taking the A 2, the total value become 8. So, it will take this particular. So, here you can see that the optimal policy is arg max, and therefore, the trajectory you can see it will take A 1 and then A 2. So, A 1 will take from A it will take the state C, and from C it will take the action A 1, from C it will take the action A 1, and it will reach the next state D. It will, and from D it will take the action to reach F, and for that it will take the action A, that is any action if it takes it will reach. So, total return is 6 plus 8 here in this case. Now, Q learning, if you see, will update the rule, that is Q S A is nothing but 1 minus alpha S A plus alpha r plus gamma times the max of Q values. So, Q learning algorithm, if you can see, can be represented here, that will require the behavior policy using random, learning rate is alpha is between 0 and 1, and discount factor gamma is between 0 and 1. So, initialize the Q table stores the Q values of each state action pair for n rounds. It will explore the observer state S and choose the action A using the behavior policy E and receive the reward R and transition to the next state. It will update using the Bellman equation. So, there are 2 things, one is called exploration, the other is called exploitation, and it is controlled by the behavior policy, that is pi E. So, Q learning implementation, we shall use this implementation to solve the optimal resource allocation problem, and it uses the epsilon greedy exploration. The behavior policy chooses the action based on the exploration probability epsilon during the learning phase, and epsilon greedy behavior can be implemented as shown in that particular code. Now, MDP formulation of resource allocation. Now, coming back to the resource allocation, for the sake of simplicity, we shall assume a private cloud scenario only. Furthermore, we shall discretize the action to make it a finite set. The MDP can be stated. So, with the states keeping E, T, D, L, that is the discrete set of 4 tuples, where E is drawn from 0 to E represents the number of available edge virtual machines, T means represents the current time slot, and D represents the number of virtual machines demanded by the user, and L demands represents the duration for which the user can occupy a demanded virtual machine. All 1, 2, 3, 4, these 4 parameters becomes the state. So, state is nothing but the 4 tuples, and these 4 tuples will have 4 different parameters in the state together define the state. Now, action A is 0, 0.1, 0.2 and so on up to 1. So, between 0 and 1 the actions are there. So, discrete sets contains 11 actions, and each representing the ratio. So, these are 11 and each representing the ratio of VMs allocated from the private cloud. Reward st, at and st plus 1 is equal to minus the cost function of the private cloud is the reward function is the negative the cost value, and initial state of MDP start from the state S1, where S1 is equal to E1 D1 L1, where D1 and L1 are sampled uniformly from within the range 1 to D, and final state ST is reached after the t time steps. So, transition function is stochastically in our MDP comes from the random user demand. We can assume the user to demand uniformly from the set of two tuples, that is D and L. So, D is from 1 to D and L is from 1 to L in the next case. In this case, the probability of the next user demand has uniform distribution over the set D. So, MDP formulation of the resource allocation, assuming that the number of VMs at the edge is 19 and the user can demand the maximum D is equal to 4 VMs for a duration of at most L is equal to 3 time slots, allocation decision has to be made over T is equal to 15 time slots. We have the total of S is equal to TDL E plus 1, that is 15 multiplied by 4 multiplied by 3 multiplied by 19 plus 1, that is different possible MDP. So, total number of possible user demand DL is 12, hence 12 possible initial states, one of which each of the user demand, the set of possible user demands is given by this particular D. So, you have to run the Q learning here in this case. So, Q learning with epsilon greedy exploration, and then you implement the policy using argmax Q values, and you have to test the learned policies and will obtain the trajectories and find the minimum cost at the private cloud over the T steps. Now, coming DDPG for private cloud resource allocation. So, deep deterministic policy gradient algorithm is the policy optimization method based on the classical actor critic style reinforcement learning. Actor is the policy network, here this one. When say policy network means it is a deep neural network which implements the policy network. So, the actor policy generates the actions based on the policies and interacts with the environment. The critic, this is called the value network, evaluates the actor's performance through the value function that guides the actor's next action, thus improving its convergence and performance. DDPG deals with continuous action spaces. So, the exploration I is managed by adding the Gaussian noise to the actions produced by the actor policy network. So, this A is given by the pi theta S plus n. Now, for critic network, the loss function is the following. So, this loss function is nothing but MSE loss between the predicted Q values and the target Q values. Similarly, the target Q value is calculated as the following using this particular equation, using the current reward, discount factor and estimate of the optimal future Q values. Actor network, the loss function is the following. So, it uses the Q value given by the actor by the critic network and also using the policy gradients. So, the parameter omega of the actor target network and the parameter theta of the critic target network are updated using the soft update over here. Now, peak DQN for public cloud resource allocation. The basic idea of peak DQN as follows: for each action A in a parameterized action space, here you can see because of x e plus x k is equal to 1, we can consider k and x k in the action function. So, here you can see that the action function contains this particular k and x k, that is q of S A is equal to q of S k and x k, both are considered here, where S is the states, k is for the discrete action selected in the time slot t, and x k is the parameter value corresponding to key. Type of public cloud instance, on demand, reserved instance, and that we have explained. Similar to DQN, that is deep neural network is used here in PDQN to estimate the parameterized key values. That means that the goal of PDQN is to find the corresponding parameter theta, that is parameter of critic network. When omega, that is the parameter of critic network, is fixed, it can be written as the following. So, the loss function of the value network can be written using this equation, and in the similar manner the loss function of the policy network can be written by this equation here. So, PDQN training steps, the input of the algorithm contains the information about the user request demands dt and the unit cost of the spot instance in the public cloud at time t, that we have already seen in the previous examples. In the beginning of each iteration of the algorithm, the edge node first needs to obtain the state S of a collaborative cloud edge environment and then pass the state as the input of the neural network into the strategy network to obtain the parameter value of the discrete action. All the edge node gets the action, it will select the appropriate public cloud instance based on the discrete values in the action and determine the number of public cloud instances to be used on the parameter values. Then interaction with the environment occurs to get the next state, reward, termination flag. Storing this round of experience to the experience replay pool, the DRL agent will sample from the experience replay pool and calculate the gradient of the value network and the policy network. It will then update the parameter of the corresponding network. After one round of iteration, to ensure the convergence of the resource allocation policy, the training will continue repeated to the maximum number of training round sets. Now, coming to the Google cluster workload traces data set, which was published in 2019. That data set contains the workloads running on 8 Google Borg compute clusters for the month May 2019. So, the traces describes the job submission, scheduling decision, resource usage data for the jobs that ran in these clusters. It has enabled a wide range of research on advancing the state of the art for cluster schedulers and cloud computing, and has been used to generate hundreds of analysis studies. The new trace allows the researchers to explore these changes. So, CPU usage information histogram for each 5 minutes slot, not just sample information about alloc sets, job parent information for the master relations such as map reduce job. Just as last trace, these new ones focus on the resource request and usage and contains no information about the end users. So, the trace data is being made available via the Google BigQuery, so that the sophisticated analysis can be performed without requiring the local resources. This site provides the access instructions and detailed description of what the traces have. So, if you see this particular type of results, so what you can see over here, EF means that edge first, and randomly select the edge node or a private cloud node, and PSOB is using particle swarm optimization optimizes the resource allocation action for the time. So, here you can see that experimental results of a low intensity groups. So, here what you will find here is the cost is being reduced here using these kind of that is edge first. It is quite effective in all the cases. Similarly, when you see the public cloud also in the use, and then you can see that the edge first plus on demand edge plus random plus random. So, here you can see that the cost the lowest cost is of the edge first, and so edge plus, that is edge first and on demand, and then other algorithms that can be designed around that particular cases. So, conclusion: in this lecture we discussed the formulation of a resource allocation problem in cloud edge collaborative way of computing using private and public clouds. We have using Markov decision process, problem formulation of resource allocation problem in a collaborative edge cloud computing, along with parameterized DQN and the deep deterministic policy gradient algorithms of a reinforceable learning to solve resource allocation problem as a decision problem. We have also briefly covered the Google cluster workload traces data sets. Thank you.